You know. Products of chemical reactions. This was the last example we did. This was a no reaction one. So what I want to do is start with one that will be a reaction, and then we'll continue on with our lecture in this series. Okay. So, oh yeah, I wrote one down, darn it. What did I write down? Oh yeah. So Na2S. So sometimes I'll give you the names that is written out, sodium sulfide, and then you have to write the formulas. Sometimes I will give you the formulas, okay? Plus FeCl3, that's ferric chloride or iron 3 chloride. And you're supposed to predict the products of the reaction. So the first thing you always do, right, the first thing you always do is you write out all the ions. Like when you're given the names, you write the ions out, and then you predict the reactants and the products. But you're given the reactants, so you still have to know what the ions are. So what's the sodium ion? Na, what? Plus, what's the charge? 1. How do you know it's plus 1? Group 1, yeah. See, these are these things that get used to thinking about where it is on the periodic table to save you a lot of time. S is sulfur. Sulfur is what ion? S2 minus, right? And then, bless you, iron is, well, you don't know. Because iron's one of the ones in the middle. So you're going to have to figure that out. So the way you figure it out is you look at chlorine, and you say chlorine's minus 1. Right? Or you uncross it, so it must be plus 3, right? So I just got that by looking at the formula and realizing there's a 3 here. Chlorine's got a minus 1 charge, so there must be a 3 here. And the chlorine, as chloride, is Cl minus. So now you can write the products, okay? And the products you get by just taking the inside and the outside. And the iron, the metal, always goes first, or the more positive thing always goes first. So I'm going to have sodium with chlorine. I'm going to have iron with sulfur. When you write the products, the order doesn't matter, like which compound goes which, so don't freak out. I'm not going to ask you questions like that. So let's start with sodium, since it's first on my list of ions. Right? What's sodium chloride's formula? NaCl. And you know that because it's a plus 1 charge and a minus 1 charge. Okay. You notice what I did here. This says Cl3, but I only wrote this as Cl minus. Why didn't I put a 3 in there? Because there's 3 of the Cl minuses. That's how the formula is made. You have an iron cation and 3 chloride ions that surround it. Okay, they're not together. Okay. It's not a polyatomic ion, in other words. So you break it up, Fe and Cl. And so what's the formula for the product? Fe and S? Fe2S3. All right, good. So now what we can do is we can determine, once we have a product, we can determine whether or not a reaction occurs. And for that, you have to grab your solubility rules. Now, one of the things I said you should always remember, and you should always just you should memorize this. If it contains something in group 1, it's always soluble. Right, no exceptions, except for lithium has a few oddball exceptions, but if it's in group 1, it's going to be soluble. So that means everything with sodium is aqueous. You don't have to look those ones up if you just have that one thing memorized. So sodium sulfide has sodium in it, right? Aqueous. Sodium chloride, well, it's salt, but you should know salt is soluble in water, I hope. Right? That's aqueous because it has sodium in it. So my states, I can fill in AQ over there and AQ there. And the group 1s come up so often, just know that.
Are you going to want us to always put the states on the exams?
It just depends on what the question asks for, yeah. Sometimes yes, sometimes no. Yeah. And I'm going to show you a couple other things with this reaction. I'm going to bypass some of the notes and just write on the board. Okay, so what's left? I got to look at iron chloride, iron 3 chloride, and I got to look at iron 2 sulfide. Handy dandy solubility chart. And I'm looking up, what do I look up? Do I look up iron? No, for this you always go by the anion, so you're going to look up chloride, and here in the chart, right, third one down, there's chloride, bromide, iodide. These are generally soluble up here. The exceptions are silver, mercury, and lead, and that's not silver, mercury, or lead, so that's aqueous. Okay? And I didn't leave room to put aqueous. I'll fix that. So it's aqueous. Now, iron 3 sulfide. Okay? I want to know whether or not it's soluble or not. So what am I going to look for? I'm going to look for iron. I'm going to look for sulfide. Look for sulfides, S2 minus. Now, sulfide falls in the bottom half of the list. Those are the things that are generally not soluble. You guys up with me on that? Not soluble. If you need another one, just grab one, okay? It's good. I like walking around because I'm not very good at staying still. Who else needs one? What's that?
You have to start smiling.
Yeah, start smiling. I'll stay here. We're doing this here. Got one, but I got it. Anybody else? This is why I'm always so tired at the end of the day. Do this kind of stuff all day long. We got it? Okay, if you need one, they're over there, okay? I'm not really picky about people getting up and moving around in class either. If you need to get up and move around, I don't really care. That's how you learn, that's how you learn. Okay, so sulfides and the things that's generally insoluble, the exceptions are what? Group 1, right? So because group 1s are always soluble, that's why it's the exception for sulfides. So what is that? Solid. It's a precipitate, right? So I'm going to put S next to it. Okay, so this is a reaction that takes place. I know that this reaction will occur because iron 3 sulfide is insoluble, or ferric sulfide.
Can you explain again how it's a solid?
Okay, so look at your solubility rules. Where's sulfide? S2 minus. Right? It's down at the bottom, right? See, this is the beauty of having this iPad thingy. It's right here, right?
Yeah.
Well, these are generally insoluble, so that means makes a solid, right? Mm-hmm. So that means this will make solids except for these ones. And then if you look up there, right, that's iron. Right? So iron up here, right? Not one of the exceptions, so it's going to be solid. If it had been one of the exceptions, it would have been aqueous and would have just dissolved. Okay?
I wasn't able to see what you said.
So I was pointing at this, right? That's not one of the exceptions.
The FE is not one of the exceptions?
Yeah, because you can look down here.
Okay.
It's not in there, right?
Okay.
So that means that it will be solid. Okay? We could practice that more. We're going to do a lot of it in lab. Okay? All right, so I should probably take one second. I don't have it all memorized. Make sense? This is the basis of lots of what we're going to do today. So I want to make sure you guys were all on the same page, at least marginally so, right? Like you know what I'm pointing at least. And what's the next thing? We'll balance it. Since a reaction occurs, we're going to balance. If no reaction occurred, then I'd write no reaction and we'd be done with that problem. But then I wouldn't have picked it as an example. So I'm going to start with this guy. You know why I'm starting with this guy? It's got more stuff in it. That's one of my like unwritten rules. Like the thing that has the most stuff in it on one side, that's what I choose. So this has got like iron and sulfur and a whole bunch of them, so I'll choose that one. So I've got 2 irons here. I've only got 1 over here, so what do I need to do?
Coefficient 2.
Coefficient of 2. So I'm going to go ahead and drop that in there. Big funny too, I know, but that's all I could have moved it again, but I don't want to. Down. So I did that. Okay, this is what I'm starting with. A lot of times what I'll do when it's the one I'm starting with, I just put a line under it so I don't lose track of where I started. So I'm going to do the sulfur next. How many sulfurs do I have on the right side? 3. So how many do I need on the left side?
3.
So how many, what do I have to do to this? Yeah, put a 3 in front of it. So now we got the problem of sodium chloride's not balanced. Everything else on the left is balanced, okay, with the iron 3 sulfide. So I got to figure out how many sodium chlorides I need. So if you notice right here, right, it says, oh, 3 times 2, I need 6 sodiums. And oddly enough, I need 2 times 3 chlorides. I need 6 of each. Well, and nice enough, it's NaCl, so I put a 6 in front of it, and I got it all balanced. If I had done that and it didn't work out, I would have been like, oh, I must have a formula wrong. Because it always works out. Maybe not like nice and easy like this, because I kind of guided you through it, right? Doesn't always work out nice and easy. Sometimes a pain. But if you get to the end and you've balanced everything and all of a sudden like one element is not balanced in a compound, then there's a chance that you did a formula wrong. And you just go back and fix it. Okay, so I'm going to tell you what this thing's called now, besides a balanced chemical reaction. We call this the molecular equation. It's not a very good word for this because they're not molecules. They're ionic compounds, and molecules are generally not ionic compounds. But the name for this type of formula is known as a molecular equation. And a molecular equation has everything written as compounds, no ions. Okay? Okay. Now, talked about this the other day. When I take an ionic compound and I dissolve it in water, right? What do the ions do? They separate from each other and they float around in the solution, right? That's how we got to the precipitate problem. So, in fact, when you're looking at this equation, the sodium sulfide in this solution, now think about it, I have a solution like this and I have a solution like this. They're 2 different solutions. I'm mixing them together, right? In this solution, the sodium and sulfide ions aren't actually together because it's an aqueous solution. They're floating around in this clear solution. Iron chloride, ferric chloride, right, would be another solution. It's actually kind of a yellowy color. And it's really a neat compound because if you paint it on glass and you fire it, it permanently stains the glass. Sorry, that was just side information. That's how you can paint it on ceramics, and then you could put your name on things, and when you fire it, it'll never come off. Okay, so it's a chemistry trick. This in the solution, even though the solution's yellow, will be clear. It'll be homogeneous, okay? And the ions will be floating around in the solution. So we have another kind of equation. We have what's called the total ionic equation. That's what we're going to write next. And in the total ionic equation, only certain things get written as compounds, and only certain things get written as ions. Okay? Soluble ionic compounds get written as ions. Okay? Total ionic equation. So I'm going to make this little note here. Soluble, and that means AQ, right? Ionic compounds write them as ions. The guys that did the lab this morning, they were like, oh, that makes sense now. We did this in the lab this morning. I didn't spend much time talking about it. We just did it. The other thing, which we haven't covered yet, but you're going to have memorized, of course, strong acids, write it as ions. And I will just define strong acids for you later. Okay, suffice it to say, things like hydrochloric acid, pool acid, battery acid, sulfuric acid, those are all considered to be strong acids. Some of the ones you know, nitric acid you might not know, but that's also a strong acid. There's about 5 or 6 of them you have to have memorized. A lot for your own safety. Just so you know, hey, I'm dealing with a strong acid. If I mix this in with this metal, it can produce hydrogen gas, and the next thing you know, I won't be here. Okay. Not I won't be here, you won't be here. Like, because it'll blow up, and you'll get acid all over you. That's happened. Okay, so what don't you write as ions? Solids, liquids, and gas. Okay? So solids, liquids, and gases, if I have solid, liquid, and gas up here, all right, I don't write it out as ions. And the only thing that's in that list is this. So I'm going to write the total ionic equation for that problem up there. Na. Okay. Now, sodium, you got to write it as an ion. You should write in parentheses after it AQ. Okay, but I'm lazy, so I'm going to show you what we're going to do. And then you also have to write how many sodiums there are. You got to keep it balanced. So how many sodiums are there? 6. Okay. And then sulfide, there's how many? 3. And I'm only doing that because it's aqueous, right? How many ions are there? 2, right? And then how many chlorides? Times 2. 6, yeah. Now, each one of those should have AQ, 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 AQ after it. But I'm lazy, so I just do this. I put a wavy line under it. Because you know what's wavy? Water's wavy. Yeah, that's my water wavy right there. So it's aqueous because it's dissolved in water. Nobody else I know does that. So if you go on to Chem 1A and you do this and your professor says, what is that? You say, well, it's aqueous because it's in water and that's wavy water. They're going to think you're crazy. Then you can say that Dr. K told me and they'll be like, oh, that makes a lot of sense. All right, so the next one, sodium chloride, right? It's aqueous. We could write it out as ions. So 6 Na pluses, wavy line, plus 6 Cl minuses with the wavy line, plus, then what do I do with the Fe2S3? I write it as Fe2S3 because it's a solid. And then, because there's so few of those, I actually write that one in. I don't have a symbol for solid. Like a straight line should be solid, right? This wavy line. Okay. So that's the total ionic equation. And you get that by taking your molecular equation and translating it into its ionic forms. If it's aqueous or a strong acid, everything else stays together. So I was telling this story in the first lab. We talked about this. Like if you bought a football ticket, right, and you went to the stadium and you watched the Bulldogs play football, would you go home and say, wow, I played in that football game today? No. What did you do? You watched it. Did you actually do anything during the entire game? Probably. Fresno State, probably not. Probably just watched it. But sorry, it depends on the year. Some years are really good. Some years are like, should have been really good. Okay. But you just sit in the stands and you just watch. And so what do you call those people? Spectators. So, or observers, as the other term came up earlier. But these sodium, look at the sodium. There's 6 of them, right? And these sodiums over here, there's 6 of them. What did they do during the course of the reaction? Nothing. They stood around and they watched the iron sulfide do its thing. Okay? So in the net ionic equation, that's the next thing you have to know. No spectators. Who are my spectator ions? Sodium and chlorine. Yeah, right? But the sulfur was sulfide, and now it's part of iron sulfide, right? Iron 3 sulfide. And the iron, right, became part of iron 3 sulfide. It's a solid. Those are the only things that you leave in. So what you can do is you can get rid of spectator ions, like sodium, and you can get rid of chloride ions, like that. Okay? And that leaves the net ionic equation, so you write all that out. So you would write in, just old school. I like putting the iron first, but nobody really cares. I like having the metal first, but 2Fe3 plus. If you wrote it second, I'm not going to dock you. Plus 3S2 minus makes Fe2S3 solid. And that's what happened in the solution. All the other stuff was just floating in there. The reason it's there is to bring, they came to the party and brought the iron and the sulfide, and the iron and sulfide had the party. Yeah, I guess that's okay to say. I want to get myself in trouble.
It's just going to be kind of a random thing because it's floating around.
Yeah, just in there. But you need to have them, right? You need to have iron because you can't have ions just by themselves in a solid form. You have to have something to neutralize its charge, so that's how you introduce it in the solution.
So if the iron sulfate would not have been a solid, then this wouldn't be possible?
Right. So if this had been aqueous, then everything would have canceled out. And basically, nothing happened. It would be a no reaction.
Okay.
Yeah.
What if you had like all solids?
That can happen too. So if it's all solids, that's a reaction too. Very few, but there are a few. If you take, for example, silver nitrate and copper metal, and you put them in a container and you shake them, there's what's called a solid phase chemical reaction, and you can get silver to coat onto the copper. All right. But it's an actual silver metal. It's a formation of silver metal from the ionic compound. But there are very few solid phase reactions that we talk about because they're yeah, you got to bring them in. You have to physically make them contact each other.
There's some way for these things to get together.
Yeah, reactions can't happen between molecules if they can't come into contact with each other. So it's a really slow reaction because it only happens on the very surface of the chemicals. Right? Geological things can be solid phase reactions. Transformations, heats, pressures, things like that. But those are all slow, right? Well, not all. Many of them are slow. Okay. I already talked about this. This is all the definitions, just what I just talked about. So we're going to practice some more. So make life easy. Okay, I just skipped all those slides where it explains. All the stuff I said is on those slides. Consider this reaction occurring in an aqueous solution. 2HBr, aqueous, plus calcium hydroxide, aqueous, makes H2O liquid, and CaBr2, right, a complete. So that's the molecular equation. Everything's written out as compounds, okay? Write the complete and net ionic equation for the reaction. And I will just tell you, this is a little bit out of place, because I need to tell you that that's a strong acid. So I'm going to say SA, not like SA, but like SA, strong acid. All right. Okay, so there's the molecular to write the total ionic equation, or the complete ionic equation. I have to write what is ions? Aqueous salts, right? Strong acids, write as ions. So what's the H going to do? That would be 2H plus 2Br minus. No, because that one's a strong acid. So that's why I had to tell you. Strong acids and aqueous ionic compounds split up. Okay? For the complete ionic. They gave us the molecular, so you didn't have to do that part. What do I do with calcium hydroxide? So what is it? Ca2 plus. And then what? OH minus. Is that exactly right? It's kind of right in concept. What's missing? The 2, so I need 2. That's aqueous. So now I'm left with the right half, right? What's that? Liquid, right? Stays together. Don't split it up. So I can just write this out as 2H2O. And then you'll put the state in. The aqueous is the only one I'm letting you drop out. And then there's calcium, and there's bromide. Right? And it's aqueous, so I split it up. Yeah. Now, Br2. This is one that gets people all the time. Should I write it like this? I'll give you options. You tell me which one's right. Which one of those is right? Top or bottom? All right, 50-50, right? Told you, it's one. Okay, calcium bromide forms when calcium ions and bromide ions get together. Now, bromide from your periodic table is just Br minus. Okay? The subscript that you're seeing here, this guy here, right? He's only there because you need 2 of them to balance the charge of the calcium. You, for the most part, will ignore this subscript when you bring it down here, and you get it to balance not by subscripts, but by coefficients. Okay? The reason people want to do this all the time is because Br2 is one of the diatomics. And so in your head, you're thinking, oh, Br2, Br2, Br2. And then you get to one of these problems, and that's not okay. Okay? So it's that bottom one. So that is the complete ionic equation. And now we need to do the net ionic equation. So that's this guy. So what do you have to identify to do the net ionic equation? Who the spectators are, right? I should hand this over to somebody. Does anybody want to kill the spectators on the tablet? No? Nobody's that brave? Come on. So which ones do I get rid of? I can get rid of calcium. And as you do this, do it from both sides. And then bromide. And I try to use, just as I'm doing this, different marks for the different things, so it's a little easier to see. But you don't have to do that. I just do it for my own mental sanity, which I don't have much of. And then I get 2H plus, okay, plus 2OH minus, those guys are aqueous, makes 2H2O. And that's liquid, so I'll write that down there. Okay, so one of the things I really didn't emphasize yesterday, but you do need to know this. When you have a balanced equation, lowest factor in the coefficients. So if you see the 2, 2, and 2, what can you do? Divide by 2.
Where did you get the 2 from? For the 2.
For which one?
For the first equation, for 2 OH negative.
So see this?
Yeah.
So there are that 2 distributes the parentheses.
But isn't that 2 goes to the CA?
No, this 2, okay, so like think about H2O, right? When I have H2O, what is the 2 for?
It's 2 hydrogen to an oxygen.
Yeah, so the subscript always is for the thing before it. Right before it, not everything before it, okay? So when you see this kind of thing here, okay? That's like saying, like you do like a let's say it's a math problem, you had 2a plus b, and then you did times 3. The 3 goes to the 2a plus b, 2a and the b, right? But if I'm adding if there's a plus a over here, the 3 is not distributing all the way over the a, that first a, right? It's the same concept. And some of you hated that example, sorry, but she has engineering background, so she likes the example, I hope. So this subscript distributes to that H. This subscript distributes to the O and the H, but not the thing before it. Okay.
So where did you get the 2 on top of the CA? You have CA 2 plus. I thought the A would go to the...
So where does calcium sit on the periodic table?
It's on the second one.
Yeah, so group 2, right? So it's charges 2. Okay, that's where that one comes from. Now, you can also get it from the idea that how did this 2 get there? It got there by crossing charges, so even if you didn't know that calcium was in the second group, it's a good guess that calcium's charge is 2 plus because there's a 2 down there. Okay? Right, but you can get it just by looking at the periodic table because it's one of the type 1 metals, group 1A, 2A, 3A, 3B, the little triangle, those guys. Okay? All right. So we're gonna classify. I'm gonna show you something new. Okay. I'm trying to things I don't like about PowerPoint. One, it's very linear. That's it. Things I don't like about it's very linear. Me, not so much so. Okay. So I'm going to talk about what we just did. We did metal, non-metal, at a metal, non-metal reaction. There's always ionic compound and an ionic compound reacting together. So let's say it was A and B and C and D. Okay? If this is the way the reaction is in the products, I do like double replacement, right? So it's A and D and C and B. So that's what we've done. Actually, everything we've done up till now has been this kind of reaction where you have a metal, non-metal, metal, non-metal. You have the reactants, and then you switch the products. Okay? This is called a double replacement or a double displacement reaction. Okay. So, ionic compounds that do precipitation reactions, most of those are double replacement reactions. Turns out another big class of double replacement reactions that you need to know are acid-base reactions. An acid-base, you guys know what acids are, right? Has H in the front. That's all you have to remember for now. Bases are things that have OH at the end, but not just any OH. It has to have a metal. So the M is metal. And this is non-metal. So this is going to be a special kind of ionic compound, has an OH at the end. But it's still a double replacement reaction. This is going to go with that, and this is going to go with that. This is acid. This is base. Okay? So I'm going to get, as one of my products, MX, an ionic compound. This guy's technically, this like the name for this, when you do it, is called a salt. It's not always table salt. It could be very poisonous. There's lots of salts. Lewis and Clark. I was thinking of Watson and Crick, and I realized, no, that's not it.
Yeah, that's DNA.
Yeah, Lewis and Clark went across the United States, right?
They took a long walk.
Yeah, they took a long walk starting on east of the Mississippi and ended up west of the Mississippi. Almost didn't make it because he found a rock, and when you found a new mineral in the good old days, if you wanted to characterize the mineral, you know what you did?
Taste it.
You licked it. Right? He found one that contained arsenic, and he licked it and got very sick because arsenic is poison. It's a salt. It's an arsenic salt, but it wasn't good for you. It's not table salt. So, but what's this other strange archaic compound? If you have M and X, you get HOH. What's HOH? H2O. It's water. And that's going to come out as a liquid. Okay? So if you form a liquid in a reaction, that's another sign that a reaction will take place because water is a very stable compound. Okay, so very quickly, let's go through what some of the characteristics of acids are. Begin, right? This is a type of double replacement reaction. It's just with an acid and a base. You predict the products very much the same way as you do for ionic compounds. Okay, so acids, you can recognize them because the formula starts with H. That's what we did for the nomenclature, right? Some organic acids, we put the H at the end, but we're not going to worry about that for now. They taste sour, right? That's like one of the things we tell you never to do. Don't taste your chemicals, but they do taste sour. Lemons are full of citric acid. They have some ascorbic acid in them. The sourness comes from the citric acid. Sour Patch Kids, all they do is they take sugar and they put citric acid on the outside, and that's what Sour Patch is. It's a nice way to dissolve your teeth. Personally, I like Starburst better. And I like my teeth better. Some acids, right? Most acids, in fact, can dissolve some metals. Okay? And bases, metal hydroxide, so that's what this is. This is a metal hydroxide. Okay? They taste bitter and they feel slippery. Okay? Things that produce this bitter taste are often known as alkaloids. Right? So if you have ever tasted, like if you drink a caffeine drink that's not got a lot of flavor in it, and you taste that bitter aftertaste, so you drink it and it's got sweetness, and then you sort of taste that bitterness after, that's that alkaloid, that's the caffeine. Okay? Your body doesn't like these things. Lots of alkaloids are very toxic. And those will kill you too. Okay, so yeah, nicotine's an alkaloid. Yeah, I believe nicotine's an alkaloid. A lot of natural products are alkaloids, and animals and insects and plants produce them as a defense mechanism. But as humans, we override that and we eat them. And we say, wow, this is really awesome. I'll explain some of that commentary later. Okay, so here are some common acids and bases just so you can see them. HCl, HBr, right? Hydrochloric, hydrobromic. You learned how to name those, by the way, right? Nitric acid, sulfuric acid. And then these are the strong bases, and these are just named like you would name any ionic compound. This is calcium hydroxide, CaOH2. Sodium hydroxide and sodium hydroxide and potassium hydroxide are often found in lye. So drain cleaner. Right? And you wouldn't eat drain cleaner, but somehow we think other alkaloid kinds of things are okay. Calcium hydroxide, one of the real common ones that's not on here is actually magnesium hydroxide. Turns out magnesium hydroxide is not very soluble, and it makes this white milky substance, which is what you drink when you have an upset stomach, called milk of magnesia. Okay? The magnesia is this part. It's not milk. Okay. So why do you take milk of magnesia, by the way? Neutralize the acid in your stomach. Okay. So you have acid in your stomach. Do you guys know which acid's in your stomach? Some of you do. It's the equivalent of hydrochloric acid. So this is what's in your stomach. Okay. Your stomach produces that to digest proteins, help break proteins down. If you get too much of that, then you're going to have an upset stomach potentially. And so you drink milk of magnesia to help neutralize that. A lot of the other antacids are things like aluminum hydroxide. Right? OH, it's a base, so it's an acid-base reaction. So, neutralization reaction is another name for an acid-base reaction. Precipitation is another double replacement reaction, and neutralization is the another double replacement reaction. This product that you get from the reaction is a salt. My wife thought this next one was kind of cute, so she put it up here. It's a salt rifle. Get it? Okay. I guess somebody had a lot of time on their hands. Probably chemistry class. Okay, so in acid-base reactions, the net ionic equation in many of them is this. And you'll notice the one that we did before, that's the equation we got in the one that we did earlier, where we got H plus OH minus makes H2O. Okay? This is only really true if it's a strong acid and a strong base. So they say many, but this is really the only instance that it's true. And I haven't explained strong acid or strong base yet, so I'll explain it to you just the next couple of slides. I'm going to skip this one. Okay. Gas evolution reaction, that's the next thing to cover. Turns out most gas evolution reactions fall in the class of double replacement reactions. So I'm going to put gas evolution. And it's not all gas evolution reactions, but it's the ones, and I'm going to make this table for you, I'll write it over here. If you have a double replacement reaction, okay, so we're talking about, it could be metal, non-metal, acid-base reactions, double replacement reaction, and this is one of the products. Or this is one of the products, or this is one of the products. So these could be products, okay, usually of an acid-base reaction, double replacement. It forms carbonic acid, sulfurous acid, or ammonium hydroxide. Turns out these are all unstable. So this is the product of a double replacement. They're all unstable and they break apart. And every single one of these, as part of the product, produces water. In part because water is stable. Now there's a table of these in the slides. I think it helps to write it out and show you how this whole thing comes together. Now, what's the other part? It's a decomposition. We call it decomposition because it's breaking up into more things. Okay?
Carbon dioxide.
This one's carbon dioxide. Now, let's say you don't remember that. Well, if you take two H's off and an O off, you get CO2. And this is a gas, H2O is a liquid. If I take H2O off of this, no, because it doesn't have a charge. Yeah, it's going to just be SO2, sulfur dioxide. And that turns out to be a gas, and it smells a little sewery. And if I take NH4, OH, and I remove an H2O, that's like taking one of these, and this whole thing over here, I'm going to end up with NH3. And this is a gas, and this is ammonia. It's what we use in a lot of cleaning sprays. So like Windex with ammonia D, and you spray it on your windows, and it makes it super clean, right? It's actually a great thing to add for cleaning. We also use it in fertilizers. We'll take liquid ammonia and just inject it straight into the ground.
It's not a base anymore
Huh?
then. It's not a base when it's ammonia anymore.
It is still a base.
Got this-
It's super soluble in water.
Yeah, it
Yeah.
feels slime,
Yeah, it's a base. Here's the thing though, as a gas, right, it's not mixed in water, so we won't think about it as a base. But it still can be a base, and it's very soluble in water.
But it just doesn't have a hydroxide though anymore. That's okay.
Yeah. But it still makes the solution alkaline.
That's what we
Yeah, it makes the solution alkaline. That's why it feels slippery. Just as a little side warning, if you use one of those ammonia-containing cleaners, you always have to have good ventilation because that ammonia gets into your eyes. You know, I love talking about eyes because everybody gets all creeped out. It's like talking about touching your eyeballs. You know, it makes people weird. It gets into your lenses of your eye and then clouds them up, and it's not reversible. So they're just going to be clouded forever unless they replace the lenses. So, which they can do now, but it's not common. My mom had it done. So. And the other gas, if this H2S, this is the one that I used to make as a child in my house and in my backyard. This is the really nasty rotten egg toilet flushing smell. Yeah. Hydrogen sulfide. Okay. So that's another one of those great things. Those are products that form or are a gas, and so when they happen, you either see bubbles or you smell it. Okay? Gas forming reaction. So this is a gas forming reaction. Sulfuric acid, lithium sulfide makes H2S gas and lithium sulfate. This is the gas of the gas forming reaction. Now, I'm going to write this out so you can see it, okay? But it's there. I just want to write it out completely. So how this problem's done. So let's say you get HCl and NaHCO3, and they say it's aqueous. And this is aqueous. Okay. This is one of the strong acids. This is an aqueous ionic compound. So you have to predict the products, okay? So when you do the products, again, you write out, this is H plus, this is Cl minus. This you will write out as Na plus and HCO3 minus. Why leave the H on it?
Yeah.
You don't have to, but it just, that's it's not one of the strong acids, so it stays together. Okay. We haven't talked about strong acids and stuff, but you could split it apart to get to the formula.
Okay.
Okay, so you're going to put this with this, and you're going to put this with this, right? And in the process of doing it, you're going to find out that you get sodium chloride. And then you're going to have H2CO3. Yep, H2CO3. And that's when you go, oh, hey, I know that one.
Rocks.
It's in your soda. It's this one. And so anytime you come up and you write this reaction like this and you see this, you say, oh, no, that's not stable. It's going to break up and give me water. And that other thing, and if you can't remember what the other thing is, you just subtract the water out of it. H2O and CO2. So that's the mental process you go through when you're doing these gas-forming reactions, okay? You just do double replacement, and then you recognize that the product's not stable and decomposes and gives you water and carbon dioxide. You're all skeptical, I know. Write it on your card. But that's what happens. Huh? Yeah. This is still the chapter. This is that last chapter still. Okay, we're going to take a break, 10 minutes. Get back. Well, getting me in trouble when I talk about these things. All right, so those are the strong acids. So what you need to remember about strong acids, when you see them in a net ionic equation, they will break up like that. Everything else that's an acid, like it's HF, is HF on that list? It doesn't break up, but it's still aqueous. Okay, so acids are aqueous, only the strong ones split up. Okay? I won't do it intentionally. I will try to stay with the strong acids when we use them on this test for reactions. I may forget at some point put a weak acid up there, so that's my disclaimer. You can call me on it later. That I did record. All right. Okay, so another classification of reactions. They're called redox reactions. And they talk a lot about redox reactions here. Here's the main thing you have to recognize about redox reactions. Charge changes. Now, all that was double replacement. Acid-base reactions, gas evolution reactions, precipitation reaction. That's all double replacement. Redox reactions don't fall in that category. Okay? There's a change in the charge in a redox reaction. And if you lose electrons, this is like definition stuff you should know. All right, lose electrons, that's equal to oxidation. And if you gain electrons, that's reduction.
We should be backwards.
So the way people usually remember it is Leo says, what does Leo say? Leo the line says, grr. Or you can spell it G-E-R if you want. But lose electrons is oxidation. To gain electrons is reduction. So that's Leo, L-E-O, says G-E-R. Or just G-R. We really don't like the E-R. Make sense? Like the definition stuff. Turns out in every redox reaction, right, you have an oxidation and a reduction. Because if you lose electrons, electrons are not stable enough to just be floating around, so something has to pick them up. So something loses and something gains. When it's metals, metals are losers. They like to lose electrons, and nonmetals are gainers. They like to gain electrons. Okay? So typically, metals are the things being oxidized. Not always.
Metal rust?
Is that?
Metal rusts?
Rust.
Metal rust for that reason?
Yeah, metal, iron. So here's an example. We'll just use this one. Here's iron, Fe solid, right? Plus O2 makes rust, which is Fe2O3, solid. This is a gas. This is greatly facilitated by having some moisture. helps with the reaction, makes it go faster. The oxygen can be in contact with the iron a little better. Okay, so what's the charge of iron here? It's a trick question. Now, what's the charge of iron there?
Oh, it's an element.
It's an element. Okay, 0. Okay, it's not an ionic compound. It's just an element. And all elements have as many protons as they do electrons. So the charge is 0 for this guy. Okay. The charge is 0 for this guy too. Because if it was 2 minus and there was 2 of them, there'd be a 4 minus charge there, right? So every element, as it's listed, has 0 charge. But here it's an ionic compound. What's the charge of iron here? 3. And what's the charge of oxygen here? Right? So iron went from iron to iron 3+. So it was what?
Oxidized.
It was oxidized because the positive charge means the loss of electrons. And the oxygen went from 0 to 2 minus.
It's reduced.
So it's reduced. So there's your oxidation and there's your reduction. Okay? So those are redox. That's an example of a redox reaction. You don't have to predict those particular ones. Right? It's actually a combustion reaction. Produces a lot of heat. You don't think about it, but it produces a lot of heat. We're going to do thermite. Keep reminding me in lab, remind me to get thermite set up. Maybe next time we get together, as part of the lecture, we'll just burn something. But we have to do it out in the grass out here. I'm not sure how they do that here. City College, it's all such gnarly grass. I can burn anything. All right, so here's another redox reaction. This is known as a single replacement. Okay. So I'm going to have a metal, let's say it's zinc, solid, plus copper nitrate, aqueous. And what the zinc will do is it'll replace the copper in the compound. So you end up getting Cu, solid, plus Zn, NO3, 2, like that. So why is it a single replacement? Because this one thing replaced one thing in here, as opposed to here, where it's a double replacement, or here, when precipitation reactions is a double replacement, you got metal, nonmetal, metal, nonmetal, or you have acid base, right? Here. So single replacement, this is the way you identify that it's a single replacement is this is an element. Okay? This is an ionic compound. And the thing, there's all kinds of them, but the ones that I'll do will just be all the metal replacement reactions. Give you another example of a single replacement reaction. You tell me what you think the product's going to be. I'm going to do zinc. You actually do this one in lab today. Plus HCl. So the zinc's going to replace what? You guys see that? Because zinc, in an ionic compound, it'll be positively charged. The hydrogen's positively charged. So this guy will replace this guy. So this element replaces this. So when I replace this here, what's the charge of zinc ion from the periodic table? +2, right? So when it makes zinc chloride, it's going to be ZnCl2. When I replace the hydrogen like this, what is the elemental form of hydrogen? It's H2. And this will be a gas. So you form hydrogen gas from the reaction. It's a single replacement reaction. You can put a lot of different metals here and a lot of different acids here. Again, this is a type of redox reaction. It's a single replacement reaction that'll produce an ionic compound and hydrogen gas. Did the attendance sheet go around? Started here. How far did it make it? It's over there? Okay. It's over there if you haven't signed in. Okay. An old professor at City College told me when he was a kid, he took aluminum and mixed it with battery acid to make the hydrogen gas, filled up a blimp with this hydrogen gas, and then they lit it on fire and set it up in the sky. Don't do that. In those days, people just laughed. There was not enough population for you to burn down the whole city. So, anyways. It's a single replacement. So it's a zinc replaces one of these two, it's going to replace the metal. So when it replaces it, copper comes out as an element, and this comes out as the ionic compound.
In a lot of these solutions, you're using something aqueous, so it makes sense you can drop it in and have a reaction. How do you heat iron the solid in some kind of container? Is it partially reactive if oxygen gas is going to?
Yeah, so that's just an iron surface, usually rust formation. You just have iron and water on top of it.
It slows, but it'll happen.
It's slow, yeah. Just like your car, like if you have a car and it rusts, right? It doesn't happen like in a week. It happens over years once you chip the paint.
So they didn't, I was wondering how you would ever find solid iron. It makes sense, it's just extremely slow.
Do you find a lot of solid iron? I think you find a lot of iron ore. You occasionally find solid iron, but I think that's not terrestrial. That's like meteoric kind of
Probably
iron.
because it's reactive, right?
Yeah, it's very reactive with oxygen.
But you can produce solid iron. Right? You can-
Yeah, we're gonna do it when we do thermite. That's that's one way to make solid iron. Yeah, it forms, and it's not slow. But one of the components of making a reaction fast is temperature. Thermite burns near the temperature of like 5,000 degrees, I think 4,000. Yeah, it's really a fun reaction. Okay, so I'm going to skip some of these. Now, the other oxidation reaction you have to be able to know how to predict. I know you're like, oh my God, one more. Yes, one more. But this one's not so bad because you already know it. So let me write it out for you. Another oxidation reaction. CH4 plus O2 gas, or let's say CH3OH, that's methanol, plus O2 gas. These are products for these that you should know, because we kind of talked about them the other day. It's a hydrocarbon, right? And this is oxygen. What do you always get? Yeah, carbon dioxide and water. That's what's coming out of your mouth. CO2 and water. CO2 and water. Doesn't matter what the hydrocarbon here is. Okay? Technically, this is not a hydrocarbon, but I'll just put it in that group. Whatever, doesn't matter what this hydrocarbon is, the product is always carbon dioxide and water. And then you balance it. And this is what we did the other day. This is also a redox reaction, though. Okay? I won't explain to you why yet, but when we get to the later chapter, I'll try to explain to you why that's a redox reaction. But all combustion reactions are redox reactions. The criteria to be a combustion reaction is that you have some substance plus oxygen produces the, let's call it X, the oxide plus heat. Well, it turns out this oxide is CO2. That's the oxide of this carbon. And you generate a lot of heat. Uses oxygen, produces heat. That's the definition of combustion. So you can actually do this. If you put iron in here, like steel wool, oh yeah, let's light steel wool on fire. Not right now. But this is one of the things, you can actually burn steel wool. People don't think like you can burn iron, but it will actually burn just because, remember that oxygen has to come in contact with the surface, and when you have steel wool that has so much more surface area, it will just light. Usually, when I was a boy, we used to light it up with a 9-volt battery. You had to lights on fire, and then you could start your fires that way. We thought we were going to like live the apocalypse, you know. Okay, so let's identify these reactions. Right? Are they redox reactions, and how do you know? Let's do the easy ones first. Look at this one. What's the charge here? 0, because it's the pure element. That's the solid here. What's the charge here? So it's a redox reaction. Okay. All you have to do is you're identifying that there's a 0 here and that there's a 3+ here. Yeah, you said it. What's this? It's a combustion reaction, except for there was no hydrogen to make the water.
That's right.
So it's just burning of carbon, pure carbon. So this is combustion, so this is a redox reaction. Right. Now, what about this one? What's the charge there? 0, right? It's just an element by itself, right? 0. Element by itself, 0. What's it here? +1, -1, redox reaction. Okay, everybody wants to call this a redox, so let's see. What's the charge here for the lead?
0.
No, it's not. It's not a pure element. It's ionic compound. So what's the charge? What's this, right? 2. What's the charge here? All right, +2. So, not redox. If this didn't change, nothing else changed. Because to have a redox reaction, right, there has to be an oxidation and a reduction. So if one of them doesn't change its charge, the other one couldn't have changed its charge either. Just to verify that, what's the charge here? -1. What's the charge here? -1. There's 2 of them, but it's -1 each. So there's no change in charge. The nitrate went over as nitrate, right? So it's not redox.
Otherwise, it would have had to go and become an element.
You know what this is, though? The reason why everybody wants to call it is a precipitation reaction. It's the one we've been doing over and over and over again. You want to call it something, it's just precipitation, though. But this is an important thing to remember, okay? The ones that we're calling precipitation, acid base, and gas forming, those are not redox. Okay? So of the kinds of reactions that we're looking at, if it is a precipitation reaction like this one is with the lead chloride, it's not redox.
There's pretty simple arguments like that. The redox has to have one element in it.
Yeah, redox right now has to have some sort of element in it, like O2 or an iron
Yes,
or
cyanide by itself.
something by itself, but it's not always that way. The ones we've looked at are that way.
This is probably a silly question, but I don't understand why an element by itself has no charge, because they have charge.
So pure, no, but this is the question. Pure element, right? Right, let's say it's like boron, right? Has 5 protons, 5 electrons, right?
Oh, so it's balanced already.
It's balanced.
Oh, okay.
Doesn't have to. It's in ionic compounds, something's got to be a gainer and something has to be a loser. Right? So the metals are usually the losers and the non-metals are usually the gainers. But their electrons and protons don't balance. That's why they have charge. So like O2, I mean the things that I point to all the time are like O2. And people, what's the charge here? And a lot of people want to say, well, it's -2, but if it was -2, then you had 2 of them, it would be -4.
And that's considered matter at that point. Matter's neutral, so it has.
Yeah, it's the element. If you don't write a charge up here, the overall charge is 0. Well, there's only oxygen in there, so each oxygen has to be 0. Yeah. Protons and electrons have to be balanced in that one. Okay. Well, believe it or not, we actually may have covered everything. This is just combustions. So just as a summary, there's this slide. Classifying by what happens. In other words, what you see going on. Okay? We've covered precipitation reactions. That's two metal, non-metal. They form a solid precipitate, right? Two ionic compounds. Acid-base. You have an acid reacting with a base. Usually forms a salt and water. Gas evolution reaction. You have usually an acid with something that decomposes to form a gas. And then we have redox reactions where the charge changes. So this is one of your things your book talks about. This is classifying reaction by what happens. But if you remember, as we were going through this, right, all of these are double replacement. This includes combustion reactions and single replacement. Oh, I just realized I should just be writing this on the slide. I'm writing it on the board. Still recording.
What's the combustion reaction also considered?
Yeah, redox.
It's a redox.
Yeah.
I mean, is there any other labels we can give as far as a reaction?
No, just combustion. Combustion and redox.
No level of replacement.
No. Yeah, you'd like to, but it's so many things can happen in a combustion reaction. Yeah. Okay. So we can do double replacement, single replacement. Okay, there's some other reactions, and what your book likes to do is talk about classifying reactions by what atoms do. Okay. And there's displacement. They call it displacement. I call it single replacement or single displacement. And there's double displacement. That's all we've really talked about till now, except for we have come across some decomposition reactions. The gas-forming reactions, I make H2CO3, I make CO2 and water, that's a decomposition reaction. Okay? Decomposition, by default, you start with few things and end up with many things. Okay? If you're doing a synthesis reaction, that's kind of the opposite. That's when you start with a lot of stuff and just end up with a few things. Okay? It doesn't have to be just one thing, but synthesis, you start with lots of stuff and you end up with just a few things. Okay, so let me skip to the very end, actually. These are just examples. I don't know if these help you that much. So again, let's just do some practice problems. We'll start at the bottom just for fun. What about this reaction? Decomposition. I got one thing and I get two things, right? That really only happens if you heat it really hard, by the way. It won't be aqueous at that point.
You gotta heat it up and put some energy into it.
Yeah.
So would that be endothermic reaction?
Yeah. This one?
It's the other opposite.
Yeah, it's a synthesis reaction. And this one? Double. It's a lot easier to do the problems than to talk about the concepts. Why is it double, right? Well, this went with that, and that went with, oops, sorry, got my arrow in the wrong place. This went with that, and this went with that. That's the whole thing that we've been doing this whole time. All right. And that top one, single. How do you know that? Because this is a,
Yes.
and that's going to replace, what is it replacing? It's replacing the hydrogen, right? Yeah. So there's an element over here, and an ionic compound.
And that's a redox.
It's also a redox reaction, yeah. Aluminum goes from being 0 to +3 over here, okay? All right, I can tell you this, we have more lecture. So that's the end of that chapter, but that covers everything that's going to be on the exam. Oh yeah, I think I just whacked it with my arm, sorry. There you go. I'm going to start in on chapter 9, 7, 8, I don't know what it is. Yeah, 8. I don't know, I lose track of the numbers. My favorite way to lecture this class is just to come in with a pile of papers and start talking. It's awesome.
All these aqueous compounds,
Yeah.
I mean, most of these solutions for these reactions are happening because these aqueous solutions are in the water, right? We found these like solids.
Some of them happen in the solid phase, but not very many.
And we've seen some, but for the most part, it's because they've ionized inside.
Yeah,
inside
in a
the water.
solution, and what that allows to happen is because the ions can come into contact with each other faster as they're dissolved rather than as solids.
As solids, would they react at just a slower rate? in
They
places where
will
they've
if the reaction is favorable. So he's asking actually sort of a fundamental question. Why do these reactions happen? And the real answer comes down to the products they form are more stable than the reactants.
been, which makes sense, which is why obviously they'd go one way, otherwise you'd have it back and forth.
Yeah, but you actually, some of these are a little back and forth. It's just so much more favored to go forward than backwards, and that's what you see. So like water, you think about water as a compound, it's very stable, so that's why it forms. When you see precipitates, they form that solid and they precipitate out in the solution. It's because that precipitate, the ions like to get together. That's very stable, and that's why that reaction.
Where else would they want that form a precipitate and then dissolve back into ions, essentially? in the solution?
Which one was that?
We had maybe station 3. We had it formed a precipitate and then it fully dissolved.
That's a concentration effect. So they probably got together at high concentration, and then when it dissolved through the solution, the concentration dropped and it probably redissolved. I can show you. I'll show you some other examples.
This, I think, I'll tell you what it was too.
Does the reaction make it go
It was a
supersaturation?
barium chloride and sodium phosphate.
Phosphate. Then you got barium phosphate to come out, but they come together at high concentration where the interface is. But once they mix completely, right, the concentration in both halves is lower, and as a result, it redissolves. But there are other things that can happen with metal ions that are a little more complicated than that. I can show you some of them. They're really easy to show you and explain kind of what's going on. But there's lots of things that will dissolve at some point and then reform at other points. Okay. All right, 5-minute mental break while I change slide sets.
One way to do that is to change the temperature, right?
You can change temperature, yeah. But there's also other kinds of reactions that we don't talk about.
Is the reaction essentially making it go supersaturated and then the reaction slows down so it precipitates out?
When we were talking about, he was saying like, so when you poured into those two aqueous, you had a super high concentration per top, so all of the new one was exposed to a small bit, which allowed for a reaction, but once it was even, it preferred to be ionized. He's gonna force the reaction on it for a second.
Yeah, these reactions, some of them are concentration dependent. So, high concentration, they precipitate. You go to low concentration, they redissolve. That's actually a topic of a later chapter. Equilibrium stuff. All right, so quantities and chemical reactions. So I'm going to give you the nice, happy version of this first. I'm going to skip around the slides a little bit. So we're going to make pancakes. We're going to talk about making pancakes. Yeah, chapter 8. So we're going to talk about making pancakes. And we're going to have, we're going to have a recipe for pancakes, which is pretty simple and basic. I don't really like this reaction. It bothers me because I don't like that 1/2. like a real chemist doesn't leave halves in their balanced equations, right? We do them as whole numbers. So that's the first thing we're going to do. We're going to fix this reaction so it comes out whole numbers. So we're going to fix it. I should have probably started a new lecture slide. But. So I'm going to change this. I'm going to do 2 cups of flour. Okay. If I have 2 cups of flour, how many eggs do I need? 4. And then I'll have 1 teaspoon of baking soda or baking powder. And then how many pancakes will I get? 10. I'm going to call them peas. Okay. That's actually more like a chemical reaction because I have whole numbers, right, representing these different substances. And these are representing the compounds that are going in, and this is indicating the product that I'm getting out. I'm getting pancakes out of the deal. Plus, I like 10 pancakes better than I do like 5 pancakes. My house? Yeah, it's 4 cups of flour. Just saying. So that's our balanced equation. Let me write this down. Let me show you how this gets used. Okay? So I have 2 cups of flour plus 4 eggs plus 1 teaspoon of soda. I'll just call it soda. Or I'll call it baking soda, so we'll just call it, yeah, baking powder or baking powder. Baking soda would be more fun. I'll call it BPs, and that's going to make 10 pancakes. Oops. Okay. I'm trying to abbreviate it, but okay. There's my 10 pancakes. That's my balanced equation. So now, let me ask you this question. This is like, seems like maybe simple. I'm going to have, let's say I have 4 cups of flour. Okay. How many pancakes will I get? 20, but what's got to be true? So here's my recipe, right? This is my balanced equation. So if I start with 4 cups of flour, and enough eggs and baking powder. I'm going to get how many pancakes? 20 pancakes. Now, mathematically, the way that works, okay, is you recognize that there's a ratio here, right? And you're using that ratio to figure it out. So if you want to know the number of pancakes, you take the 4 cups of flour, and you know that there's 10 pancakes for every 2 cups. Is that right? Okay. That's going to give me 20 pancakes. But believe it or not, this is how chemical reactions work. That if you want to know how much stuff you're going to get out at the end, it's like cooking. You have a recipe that you're following, and you use the proportions in the recipe to figure out how much stuff you can get out of it. Okay, now, in a chemical equation, though, this 2 cups of flour is really moles, right? Because when we balance the equation, it's a mole of this and a mole of that makes moles of product, right? So this is treated as moles in a chemical equation. Dot, 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 all these are moles. That means in order to do this calculation in chemistry, you've got to get to moles before you can figure out how much moles of product you get. We're going to cover those details when we get back. But I want to talk about one other thing, okay? I assume that I have enough of everything else here, but let me ask you a question. If I have 4 cups of flour, and I make all those pancakes, How many eggs did I actually use? 8, right? How did you do that? Well, the proportion's still the same, right? So if I used 4 of these, I would double this. I would have to double that as well. Mathematically, the way we do it, okay, is we would say, well, I have 4 cups of flour. And then for every cup of flour, or every 2 cups of flour, it's 4 eggs for every 2 cups of flour. That's the mathematical relationship that's in the chemical equation, my pancake recipe. Carry out the math, that comes out to be 8 eggs. What if you only had 7 eggs? What would happen? Pancakes wouldn't be so good, right? Wouldn't come out right. You wouldn't have the right amount of eggs in your recipe. It would come out different.
So you need to cut back on the flour.
Or you would have to cut back on the flour. Now, if you were like me and you were doing this, you would just like take the scotch out and just not put it in there. You know, just dump it out. Realize that you don't have enough stuff. Okay. So let's look at this a little more detail again. Okay. You know what I'm going to do? I'm just going to kill the slides for now. I'm going to write on the board. I'll still record what's going on. But I think it's easier to understand this if I just write it down. So this is my balanced reaction. Right, these are my reactants. And this is my product. So, I'm going to define some terms for you. These are definitions that you need to know. Your theoretical yield. What does theoretical yield sound like? How much you think you can get, right? What you could get if it was a perfect world, right? Like if this was cookies, it would be that, oh, you're going to get 2 dozen cookies out of your recipe. In reality, in my family, they just eat the dough. You get like 1 dozen cookies out, right? So there's a theoretical yield. That's what the recipe says you could make. And then there's the actual yield. Theoretical is how much you make if everything goes okay. In fact, everything has to go perfectly. Right, that's not the book definition. That's like, that's a good practical definition. If it goes perfect, man, you get it. It's like my cousin owned a bike shop, right? And we buy bike frames, and you buy the wheels would come in the box. And in theory, for every box of bikes and bike parts, you'd get a bike out, right? What happened in practice? Well, you pull one out, and it turns out like a gear or a spoke got bent in the shipping, and so that would be not the theoretical yield. The actual yield would be 1 whole bike less. You get 100 bikes, there's going to be some bikes that are screwed up, right? Same thing happens in this, right? Ideally, I'm going to get 10 pancakes for every 2 cups of flour. That's what my theoretical yield will be. Your actual yield, well, this is real life. This is what you really get out of the situation. Okay? Okay, so percent yield equals, I'm going to call that A, I'm going to call that T. All right? Actual over theoretical times 100. That's your percent yield. Most chemical reactions we use in Chem 1A, Chem 3A, a lot of them in 1B, we designed the experiments so that the theoretical yield is, right, the percent yields, right, the percent yield is close to 100%. Because we don't want students to do a reaction and say, this doesn't work, I only got like 10% out. But 10% can be a theoretical yield. You think you're going to make 10 pancakes and you only get 1 out, okay? That's not unusual in chemical reactions. But we like people to make a lot of stuff in 3A, so we just give them stuff that works. That's another way to look at it. So, scenario, okay? I've got 6 cups of flour. I've got 10 eggs. I got 2 teaspoons, right? Yeah, teaspoons of baking powder. And assuming you have to conform to this equation, right? How many pancakes are you going to get out? So that it becomes, you have all these proportions you got to start working with. It gets to be a real pain. So this is what you do. Like, this is the way chemists treat this problem, okay? I have 6 cups of flour. I know I get 10 pancakes for every 2 cups. Keep doing that. So I'm going to get 30 pancakes, okay? At least if everything went perfectly with the flour. Again. With 10 eggs, let me write it up high. There's all this stuff in the front of the classroom. I said 10 eggs, yeah. How many eggs is it for 10 pancakes? 4, right? And you got pancakes called. Yeah. So this is going to come out to 25. Did my math right. Okay. And if I did have teaspoons of baking powder, so 1, what do I have? 2 teaspoons? 2 teaspoons of baking powder. It's 10 pancakes per teaspoon. That says I can make how many? 20. Okay. When I make the 20 pancakes, I've used up all my baking powder, right? Am I ever going to get to 30 or 25? No. Because this quantity limits the amount that I get out. And so I would say, I only have 2 teaspoons of baking powder. All the stores are closed. I can't go out and get more stuff, and my neighbors don't like me. So, that's not true, but let's pretend, right? I could only make 20 pancakes, and then I'm done. Okay? So, this is now my theoretical yield. Now remember, in chemistry, we'd be doing this as moles, but like it applies in the real world. I have this recipe. I have different quantities of everything. This is going to limit how many pancakes I have. I can't make 30. I'll have just a lot of flour left, and I can't make 25, right, there'll be some eggs left. Okay? So this is the theoretical yield. This is my limiting reactant. And the limiting reactant determines the theoretical yield. These guys, these are known as excess, which chemists often abbreviate as XS. Yeah. Because we don't want to write so much. You guys get the concept, how that works? I'm just cooking. That's what chemists do. We cook stuff. Oh, that sounds bad. Because that's what crack people do, right? The meth people, they're going to cook. It's a whole different thing. I'm cooking pancakes. I'm not doing meth.
It's not different, you know.
But it's really not that different.
It's the same thing.
I got reagents, right? Now, the meth dealer, he's pretty good at chemistry, actually. He knows exactly the quantities he needs to put in his soda bottle before he shakes it and makes his batch.
It's not the whole 10 that's access, right?
What?
You just subtract it.
See?
The 10x is not the access, right? The extra. So you
Yeah.
have to deduct and whatever left is the extra, right?
Yeah, this is known as the excess reagent. How much is left you could figure out because you know you're going to use up a certain number of eggs, you could subtract it out. And if you're running a business and you're doing this, right, what you really do is you figure out what you're using up and how fast you're using it using, this is called stoichiometry, and you reorder those things so that you don't ever really run out, right? Chemists' process work the same way. We add chemicals so we don't really ever run out, right? Yes. No, this is just a start date. Wait. Yeah, this is just a start date, yeah.